All right. So just a quickie on where we are, where we're going. Okay, I'll get that key already. Okay. I guess the first thing, I probably should have done this before I turned on the thing. Is there any other work to be turned in before I return these things? Sorry to interrupt your lunch. Okay. Okay. You want to take it now or later? You can if you want to go. I think the room right through there is open, but yeah, that way I could return these. Now I can't return your research papers because they periodically ask for samples of student writing. I think I've returned everyone's first lab and first test to you, second lab and second test to you. Okay. Is anyone else turning in Lab 3, the phases of the moon, today? Is anyone else going to turn that in? Did you just turn it in, James? Okay. So let me... You don't have to go anywhere yet because I haven't found it yet. Okay. I'll get it down in just a second. All right. Everybody's turned in phases of the moon. So here's yours, and yours. Okay. So that's Lab 3. Lab 4 was actually the trip to the planetarium, so there's nothing to return there. Now, properties of common minerals. Did you just turn that one in too? Okay. Here's well, 5. Give her a staple copy. She rips them apart. Okay. Okay. And if there's anything I missed, I may be thumbing through this too quickly. Please let me know. Density of igneous rocks, I just saw that one. So here's... Well, it'll be sometime over the weekend. Test 5, is that the one you were going to do? Okay. Okay. So if you want to... No. Oh, yeah, that's it. Yeah. Okay, you want to go? I do. It's not a great one, but it's doable. It's a mechanical thing. Now, where you go? Or you want to... you can either go to the office, either office, or the room next door. Okay. Here's the test 5. Okay. Latitude and longitude. Now, and maybe some of these I haven't graded yet. Sorry about that. Did you just turn this one in too? Latitude and longitude.
Yeah, I think that's how I get it. Do you have any questions?
No. That was the density of igneous rock.
Oh, yeah, sure.
This is the one that you look up latitude and longitude of different cities. Got that? Very good. All right. Now, building Earth's surface, I know I've graded, I may have even returned them to you, I don't remember. But here's the topographic maps. I only only have I returned the others for some reason? Maybe I haven't graded the others. Okay, but if you haven't turned this in, have you? Okay. What's that? Okay, I must have given them back there. What's that? Okay. Well, I may not have graded it yet. I think that's probably the case, because from last Tuesday, not this week, but the week before, I've hardly graded anything since then. So I think, yeah, you had turned yours in, and I got it graded before you left the lab, I think. And then I got Brian's, and the others are in here. Okay, test 7. For some reason. Okay.
Is that the last one?
Yeah, I think I returned the others. Did I return y'all's test 7? Yours is the only one I've got. So I think I must have returned those. Okay, yeah, and that takes us up to now, because the next one is our weather test. Okay.
I turned mine in. I put it up there on the desk.
What?
Last period. I guess that was a take-home test.
Yeah, the thing is, yeah, everything that's been turned in since last Tuesday is there. Okay, this is all my classes. I have hardly had a chance to do any grading. I mean, every moment that I can, I'll zap something out, but I don't think I've had a sit-down time that I've been able to grade more than 1 or 2 papers before something else has happened. Because I had that big planning hearing that I'd been collecting data for, really all year, but mostly in the last couple of months. And some of my instructors had not yet gotten me the stuff. So last week I called them. So from last Tuesday, I got some grading done. Wednesday, I was in class all day. Every Monday and Wednesday, I'm in class from 8 in the morning until 9 in the night, with 2 20-minute breaks and 2 10-minute breaks. I can't get anything done in those breaks because I'm trying to eat something in and just exchanging stuff or setting up a lab or something. So Tuesdays, Mondays, and Wednesdays, nothing at all. So last Thursday, all my office hours that I wasn't helping students and registering and stuff, and several came by, I was trying to get ready for the planning hearing and contacting the instructors that hadn't gotten me stuff. So I got most of that done, except this one instructor. He said, I'll send it to you tomorrow, which was Friday. So I had to work on it Friday evening and Saturday, what he sent me. But he said, it's just the data, I'll get you the documentation next week. Well, I got his data worked up, so I turned in the report electronically Sunday evening. Came in Monday, was busy all day long, and I still didn't have his documentation, so I had to go to the Birmingham campus first thing Tuesday morning before our hearing at 10, and I got his documentation, and actually he was late bringing that in too, but while I was waiting on him, I got maybe a paper or 2 graded, and then the student came by for registration, and then another instructor came by, so it was just kind of, or advising, not registration. It's just been crazy. So of course Monday and yesterday were packed. Tuesday I thought I was going to have time, but I had the hearing in the morning, so I didn't have any office hours then. And in the afternoon, when I thought I would get some grading done after our class was over with, I had to get the last test and labs done for 2 physics classes, and students came by, and basically I got maybe 1 or 2 papers graded. That's all I did up Tuesday afternoon. So this afternoon, after this class is over with, I know I've got that student who came by here, and maybe one of the others, but after those 2, that's all I'm doing is grading. And I'm taking anything I don't get graded home with me, and this weekend I'm finishing it up. So when you come to take your final, I should be able to give you everything back. But sorry I don't have it graded now. But if you want to come in Monday and pick up something, I should have it finished Monday. Yes?
final, would it be safe to study all our tests?
Yeah, that would be a really good thing to do. If anything, scan and try to pick out what you think would be the top, I would say, 5 things covered in each chapter. Just sort of focus on those, and I bet you'll hit just about everything. It will be not multiple choice like most of your tests have been, but it's going to be matching. So I think it will be even easier to deal with. So you're killing bugs, huh?
Yeah, killing your mosquito you brought in.
Oh, I see.
He came in right with you.
Yeah.
It's work.
You have to take the lid off and rub your hand on the bottom of it. That used to work, and I think enough students played around with it that it got it so the pumper doesn't pump anymore. Okay, and it's pretty old itself. Okay. So, all of you turned in your research papers. I've returned most of your work to you except the stuff I haven't graded. Like I said again, if you want to come in before the test, either Monday or Tuesday morning, to pick up any remaining items you got, so if you want to study those for the test, I should have those all graded by, hopefully, I'll get them all graded this weekend. And hopefully a bunch today, but we'll see how that goes. Okay. Yeah.
The final is Tuesday,
The final is Tuesday.
along with this test.
Yeah, the test on this chapter and the final. Final is in 2 pieces. First part is the last chapter test, and the last part is the comprehensive. And, well, it's in 3 pieces. Pizza, then the 2 tests, okay. And from what I remember, 1 pepperoni and 1 meat lovers or something like that. Okay. Whatever Little Caesars has, it may be 3 meat or something like that, but it's the closest they got to that. Okay, now, and by the way, if you are coming in on Monday, remember I'm in class. It's a class day Monday. I'm in class from 8 in the morning till 9 at night. However, if you want to pick up stuff from me, here are the best times. 10:40 until 11, 1:40 until 2. And sometime before 5:30, say 5 to 5:30, and sometime after, say, 8:30. Because I don't think all of my classes will take, well, the first times I gave you were the 40 minutes I have in between the first 2 classes and the second 2 classes. And then the other times I think we'll be finished with those classes early. So that's why I say before 5:30, like 5 to 5:30. I'm really pretty sure we'll be through with those classes early. And then the second class usually goes to 9. I think we'll be through by 8:30 anyway, maybe even earlier. So if you do want to pick up something, try to hit those times. But if I'm in here teaching, we'll come by, and if they're doing a lab or something like that, I can run down and get the papers for you. Now, sometimes we meet in here for the lab. Sometimes it's 2:53. Sometimes it's 2:52. Sometimes it's 2:59. So if I'm not here or my office, try one of those rooms too. Okay. And I've already asked you about student course evaluations. Okay, so I think we're ready to continue where we left off last time. We were talking about weather fronts. I think we had started this slide, but let's pick up where we left off. What a weather front is the boundary between the air masses at different temperatures. So the first is if we've had, like we have now. Now this isn't likely to happen now, but if it were. We've had several days of pretty warm weather, okay? The warm air has settled in. Now, if for some reason there's a cold air mass comes down from the north, usually a continental air mass coming down and hits against this warm, moist air that's here, that would be called a cold front. The cold air mass moves in, and this happens more in the wintertime, of course, moves in and displaces the warmer air upward, forces the warmer air up, and then you have an unstable situation. the moist air rising is cooled, leading to large cumulus and thunderclouds. And I think that's, well, no, we talked about that map, and this was the description of that. The cold air mass comes in, the warm air is sitting here, comes in and forces the warm air up over the top, and that creates large cumulus and thunderclouds. Now, the other way would be if you had cool air, dream on, in the summertime, sitting on you, and here you had some warm air come up from the Gulf, that would be a warm front. The warm air mass advances, but you see the cooler air is denser already, so the warm air goes over the top, okay? Now, when that happens, you get a long, gently, so you see the cold air mass has a pretty abrupt front, bulldozing its way and forcing the warm air up, warm, moist air up. That's what creates the instability. When the cold air is already in place, the warm air just slides over the top, and that's a longer, more gently sloping front. This is the one that the slide doesn't show up. It should be there, and in your text, this would be figure 2311, I think. Okay? And long, gently sloping front. The clouds of the rain may form in advance of the front. You don't realize the front's gotten there because the cold air is in place. It comes up and goes over the top, and you get the moisture then. And if it is strong enough, it makes the other retreat, and then you have warm air in front. And the third type of front is a stationary front, and these are forces influence the warm and cold air masses. They get balanced, and they just sit there. Now, I'm trying to think if this has happened this year somewhere. I'm sure it has. I just don't remember where. Someplace that had lots of flooding this year.
Did you see what happened yesterday in Mistaken?
Karen showed me a picture of that, and I was just amazed. Yeah.
And I was at the Hoover Library, but it was just down the street from that.
Right.
Over by that holiday bowl, Vestavia.
Yeah.
There were cars just floating.
That's what she showed me pictures of it, and one of them floated into a creek that was floating out of the creek. That was unbelievable.
Yeah.
It was like a storm, and then it wouldn't move. It just sat there.
It said that, yeah. It looked like something was going to happen here. In the morning, it didn't seem like there was much chance of rain. I didn't hear of any chance of rain, and I left my windows cracked because it was so stinking hot, already in the morning. So I left my windows cracked, and when I was teaching a calculus class, Calculus 2, and Mr. Hollins came by and said, it looks like it's so stormy, your windows are cracked. Oh, that's right. Because I can see the big clouds there, but it hasn't started raining yet. So thank you. That was very sentimental pencil there. We had gotten it for our, we had an Italian kid live with us one year, came and did his senior year in high school. He was a U.S. citizen. His parents had moved back to Italy, and we were friends with his parents. And Karen got all this stuff for him for his senior year, and a bunch of mechanical pencils. He said, I like the wood ones. So we have a bunch of mechanical pencils. So I'm really tied to that one. I think of Jock them up every time I see it. Okay, so I wonder if that was sort of like you said, it started and it couldn't move. So I wonder if they were little fronts that came together and just dumped on Vestavia. Now, I wouldn't have thought that was the case, but it could have been. But that has happened sometimes. Trying to think if it happened here earlier in the year, that we just had day after day after day after day of rain. I know that's happened, and it may have been that was a stationary front deal. Okay. And there must be several slides that are not showing up here. Okay, here's the one. This is what happens on the cold front. Okay, the warm air is in place, sitting there. Nice, moist, got plenty of moisture in it. Here comes the cold air. It pushes the warm air and forces it up over the top. Notice how steep it is. And that that cold, warm air being forced over the top, because the cold front's moving, that creates the turbulence here. And that's why you can get tornadoes sometimes. That's why you get in these huge cumulus clouds. Look at that. That's going 15 kilometers into the air, okay? That would be about 9 miles up, okay, that cumulus cloud. And if they get that tall, you better believe there's some ice up here, and that's coming down. Now, in this warm, hot summer, most of the time that all melts before it hits the ground. But if they have gotten into a pattern of, icing up, trying to fall, and then you get another current taking them back up, it gets more ice, and they get big enough, then they fall as hail. And that can be really damaging to crops. That happens a bit more in the spring, I think, than in the summer, but you can't have it in the summer. I hate when it happens when the peaches are just coming, still on the tree. That hail can damage peaches really badly, and I love my peaches. I was just eating one right before I came up, and a couple of those last years came by. Okay, so that creates some of the big cumulus clouds that really create heavy thunderstorms.
You say you're from Georgia?
I grew up in Georgia. I was born in North Carolina. We moved to Georgia right after I turned 40 years old, and I lived there. In fact, still have land there.
And what do y'all do to the beaches over there? Them things about that big. You don't get them that big here.
Well, I don't know. The main highway down our county, we don't live on it, but we're not too far from it, about 3 or 4 miles from it, is Highway 25, US Highway 25, and it's called Peach Orchard Road. And it used to be you drove down that road, you see peach orchards on either side. Not continuously, but as you drove down. And I do not know of a single peach orchard on that road anymore. They just over-farmed it, and a lot of them went over to either South Carolina or came to Alabama. But actually, I prefer the smaller peaches. The big ones look really pretty, but sometimes the flavor is sort of diluted, it seems like.
You been down to Clinton?
I have been down there, yeah. Used to, when my wife's family would go to the beach, we hoped it would be at the time the beaches were coming in, because we'd stop there. But we go to the Pepper Place Farmers Market just about every Saturday, and all the farmers bring theirs in there. So we eat them not quite right off the trees, but when I was growing up in Georgia, we would go, my dad liked to go pick peaches. We'd go to these orchards that let you in after they let all the truckers in and everybody else. You go in and just pick up little things, and boy.
Y'all got some huge peaches over there. They got this big.
Yeah.
And they don't make it here because Georgia is here.
Georgia was named the Peach State, but I think both South Carolina and Alabama outproduce Georgia in peaches now. They still call themselves a Peach State. In the Peach Bowl, Peachtree Street in Atlanta, peach everything. So that's the case with the cold front. Let's see if they show the warm front here. Yeah, here's the warm front. This time the warm air is coming in, the cold air is already in place, and the warm air just climbs up the top and sort of makes a gentle slope here. And as the warm air goes up, the cold air condenses the moisture, and you have things. But look at these thunders. Those are still cumulus clouds, but look at those. 4 kilometers high. That would be 2.5 miles high. Nothing like the 15 we saw before, or 9 miles high. So it was just incredible difference here. And you see, you get the rain before you get the warm air, because the warm air is grown up on top of the cold air, and that's what creates the rain. Then after, if the warm front does push it on through, you usually don't get much rain after that. So the rain precedes the front approach there, whereas here it precedes it a little bit, but I mean the front's right when the front gets there, that's about the time the rain starts. A little bit ahead, some behind. Okay. And I don't think they show anything like a stationary front. All right, before we move on, and this is where I think I had planned to start today, because I thought of this right at the end of class last time. There's a little blurb at the top of page 581 on Science and Society, the urban heat islands. Have you ever heard of that before? Okay. I experience this most afternoons, evenings, driving home. I will go out here and get in the vehicle. There's a thermometer in my thing. I can see the temperature there on the dashboard. And I'm just going to take her around, like last night around 9. Let me see if I can remember. No, I didn't really pay attention to it. But let's just imagine that it was, say, 79 degrees. That sounds about right. When I left here at 9:15, 9:30 last night, around 79 degrees. Got in the vehicle and headed up the expressway. Now I'm going a little bit north, I'm going a little bit east, and it's also getting later in the day. So when you're heading north, you expect the temperatures to fall. When you're heading east, after the sun is set, the sun set there a little bit before it sat here, not much, just a couple of minutes, but if anything, you expect it to be a little cooler because the sun's been down a little longer. And it's taking me longer to drive there, so it should be getting cooler as you go. So I get on the expressway and start heading up. Maybe the temperature is around 79 degrees. And sort of about the time in between Vesper, there's a little bit of space in there when there's not a lot of city around. It may actually drop to 78 or 77. Typically it does drop a couple of degrees. But then once I start heading into Birmingham, it starts going up again. And that's because, if you think about it, a big city, okay, bigger buildings, all those buildings are air conditioned, okay, so they're cooling the air inside and blowing the heated air out, you know, when the compressors have heated. So that's happening. A lot of the land is paved, either blacktop streets, parking lots, whatever, reflecting, you know, you don't get a lot of absorption there. Whereas out here, all the grass we have here, there's a lot more, that will be cooler. Trees are cooler. Buildings are not cool, okay? And then you have more cars and buses and everything else spewing out exhaust, which is heated. And you just have a greater concentration of everything. So that forms what they call the heat island effect. Okay? Now, in the older days, you also had smog contributing to that. Nowadays, there's a little bit less smog, though we still have some air pollution. Certainly have some. But all that smog and stuff will trap the heat as well. So it was even worse back then. But I can remember it was, what kind of year was that? It was baseball season, I remember that. So it was probably about this time of year. I was driving from San Francisco to San Diego to take some naval training, you know, schools that they had me going to. I was driving down, and it had been a pretty pleasant trip. And I kept wondering, I should be in Los Angeles pretty soon, and I was going up. I thought, this is, you know, the elevation's increasing here, what's going on? And all of a sudden, my eyes just started stinging. I thought, what in the world is going on here? Was there something in the road back there that I didn't see? That, you know, I went over some chemical or something? Boy, my eyes are aching. Well, I've been driving for several hours. California is one long state. I was only going from midway down. It took me almost all day, you know. Well, went on up, and when I finally crested the ridge there and came down, there was Los Angeles. And all I could see was this orange haze on top of Los Angeles. I thought, that's what was hitting my eyes. It was bleeding over the mountain. And I drove on down, and miserable. I mean, and what's more, here's why I remember it was baseball season. They're just getting ready to play a game. I don't even remember what the teams were. The game was just getting started on my radio, and it took me an entire 9-inning game to drive through Los Angeles. The traffic was so bad, such a big, sprawling city, and I thought I'd never get out of there, listen to the entire game. As I was leaving, the game was just getting over, and it was just coming on, and I pressed that little button. Oh man, but I never want to live here, you know. The weather's great, but boy, the air pollution and the it traps the heat in there. So yeah, urban heat islands, they're real. Read this, there's several questions, well worth a thought or two. Okay, now, waves and cyclones. That's the next topic. This is on subtopics on page 582. The mechanism of this, and let me just tell you basically what a wave is. We will hit portions of them here. They happen more and more of the tropical areas. This is where most of our winds and weather come from the west. I'm pointing in the wrong direction. West, okay? Most of it comes from the west, okay? But every now and then we will get a wave that comes from the east. Very usually warm, moist air coming from the east. It's coming off the equator and coming up the eastern. And it's basically a big warm front coming in that way. Well, all the other weather is coming this way, so what you have are these bulges or waves often form between oppositely moving air masses. Warm, moist air coming from the east, and typically somewhat drier and possibly cooler air masses coming off the continent here, and they form from oppositely moving air masses. The overriding uplifted cold air produces a low pressure, okay? Now, most of the time it's the warm air that wins and that goes over the top, but if the cold air is uplifted, that really is an unstable situation. That produces, and actually, here's what they really mean. The cold air comes in and begins warming, and that's what lifts it, okay? And that forms a low pressure area. Further cold front motion leads to an occluded front, and that leads to the cyclonic storm. And these are the graphs they use, and these I do not find all that clear. Okay, they're nice little graphs, but making out what they're talking about is a little tough. Now, number one, they don't tell you why the cold air wound up on top and the warm air on the bottom. Usually that's not the case. It goes the other way. But maybe just because that waves came in and forced itself under, I don't know what their rationale is, but that's what they say happened. Well, if that happens, the warm air is trying to rise and the cold air is trying to go down, and you get these what they call bumps. That's what they mean here, bulges or waves coming in. The warm front is this side, as the warm air is pushing this way, and the cold front is this way. I think that's why that's it. This is the cold front, this is the warm front, okay? Yeah, warm front is here, cold front is here. Again, the arrows and stuff are not particularly clear. They're opposing each other, and they're creating some disturbance. So this creates this bulge or wave, okay? Warm front trying to go that way, and the cold front trying to move this way. Well, when that happens, especially when this warmer air is rising and the colder air is dropping in below it, then you get that warm air rising, cold air dropping in below it. That gives you a low pressure point right here. Where that warm air rises, cold air is trying to go down, you get a low pressure right in here. And that creates what they call an occluded front. And that's the one that they have their definition, unless this new edition does a lot better at it. Here it says, on the bottom page, first column, 582, an occluded front is one that has been lifted completely off the ground into the atmosphere. The disturbance is now a cyclonic storm with a fully developed low-pressure center. So this low pressure that was starting forming here, now it's lifted it up, and you definitely have rotation. So this is your occluded front that the cold air is moving around, whipping underneath. The warm air is trying to push its way up, and that creates some rotation. That's ultimately that low pressure area. Now, that's typically what forms your low pressure on the map. If you go back, remember this slide here, this low pressure up here, more than likely you had that kind of activity happening. Now, it's not enough to tell you here, but I'm guessing the cold continental polar air was moving down like this, and you probably had some warm moist air moving up like this, and that created the problem and the uplift, and that gave you your low pressure area, and that gave you the intense weather they're about to get, in fact are getting. Anytime you see those isobars, those barometric pressure lines, very close together, that means there's a big gradient there, and you have high wind speeds, okay? And that was the type of low pressure that is formed there. And it's up off the ground, okay? Now, the cyclone is that low pressure area with inflowing upwardly forced winds, okay? The low pressure sucks winds down, and then they move up. And as they move up, they get the rotation. Remember, I think we talked about briefly the Coriolis effect. It's an effect caused partly by the Earth spinning, partly by upward motion, and you get a torque of a motion there, and that's what creates, yeah, there it is right there. The upward force wind, the circulation pattern is caused by the Coriolis effect. And that's the one, I think I told you about my physics professor who went to meetings in Buenos Aires. No, Rio de Janeiro, I think it was, Brazil. And party city of the southern hemisphere. And he couldn't wait to get in and go flush his toilet. Okay, because he wanted to see the water flow in the opposite direction. Now, the anticyclone is a high pressure area, okay? And the cyclonic thing, notice the low pressure area, the air turns in a counterclockwise, and this is because of the Coriolis effect. And high pressure area, when the air is moving down, then you have clockwise flow. Typically, your high pressure is going to be clear skies, and with clear skies, you have sort of extreme temperatures. In the summertime, that can be very hot, not as humid, but very hot because you don't have any clouds to give you shade. And in the wintertime, clear, cold days. And if they're at night, even colder nights if you're under high pressure, okay? Low pressure, those tends to be more cloudy, so it moderates the temperature some. That's when you have your severe storms. So the anticyclone is a clockwise flow, and that will be high pressure area. The air sinks, is warm, and the relative humidity is usually lowered because you're warming colder air and its humidity is less because it can't hold as much when it's cold. When you warm it up, now it's warmer but drier air. So usually you don't get much precipitation with a high pressure. Their figure in the book, which I think is, well, they have both of these in there, but it's a, let me make sure they don't have, no, they don't. Figure 2314 is a really good show of what's going on with the high and low pressure areas there. All right. Now, what these show are some of the common tracks that your cyclonic storms typically take. Okay, cyclonic storms usually follow principal storm tracks across the continental U.S. in generally an easterly direction, from west to east. This makes it possible to predict where the low pressure storms might move next. Okay, because they tend to follow these patterns. You have one that flows from the Gulf of Mexico, basically going up the eastern seaboard, but usually out to sea. But remember, if you do have counterclockwise flow in the low pressure, that's bringing moisture back into the land. And you can usually get some pretty rough weather there, even if you're not in a cyclone. This part of Florida is going to get it pretty good because there's a lot of energy from the warm Gulf of Mexico here. It goes across southern Florida and southeastern Georgia, northern Florida and southeastern Georgia. This is a track that seems like it's been happening pretty regularly around here. This one that comes across Texas, Louisiana, Mississippi, and comes in here. Remember that line of storms we had back in 2011? That was following this track pretty closely. This used to be a real powerful one. I'm sure it still is. But in fact, I can remember when I was younger, it seemed like Oklahoma and Texas were getting the worst of the tornadoes. It seems like that's moved south a little bit. Is that global warming? I don't know. Okay? You have another band that comes here. This is another pretty, Oklahoma would still be close enough here. This would be Kansas, Missouri, Colorado, Colorado there, coming across there. This one a little bit further north, tracks like that. And these are just general, they're not always the case, but they're generalizations. Okay? And it seems like to me, and maybe it's just recent and maybe just random, but boy, Oak Grove has had more than its share, it seems like. Or some of the other communities that have been hit repeatedly in the last decade or so. Pratt City got it this last round, but yeah, it really does seem strange that it seems like it follows all the same paths. And for some reason, I don't know if the heat island effect or something, it seems like they missed Birmingham. Maybe I'm talking too soon and just my saying it's some jinx them. But the one that went through Oak Grove, they had us go into the basement, that kind of stuff. I think I told you about that. And later I called home to talk with Karen. She said, literally, it was aiming right for Birmingham Airport. Boy, think what a tornado could do to an airport. All those planes that sitting around and stuff like that. And she said right before it got there, it left the ground, got over the airport, and came back down and did more damage to the east. And she said, we were so lucky. And our neighbor said she actually could see look out the back of her house, and she saw the storm and thought that's what she was seeing. And later when she heard it, she said, that's exactly what she was seeing. It actually lifted off the ground and missed it, but then later came back down. Yeah, it's the patterns, and I wonder if all the mountains around maybe they'll break it up some. But is Oak Grove sort of down in a valley type area? Yeah, okay, so that may be true. I don't know, but it does seem to follow patterns. Okay. Maybe that's where this next slide should have been, but it didn't show up. Oh, wait. Yeah, we got all that. Okay. Now let's look at major storms. This is the next subtopic after waves and cyclones. Major storms are usually rapid, fast, violent weather changes. Okay? These things that come on slowly and gradually, even though you might get lots of water and stuff like that from them, that's not considered. These are things that come on rapidly, somewhat suddenly, and usually are pretty violent in their nature. Often associated with the fronts, the frontal passages. You can see it sometimes on the weather map. You see that front coming in, and there's just storms all up and down along that front. Three major types: thunderstorms, then tornadoes, and sometimes tornadoes are spawned by thunderstorms, and then hurricanes, and sometimes tornadoes are spawned by hurricanes, and sometimes hurricanes also produce thunderstorms. In fact, quite often, most of the time they do. So those are the three big ones, but realize there is overlap between them. This book loves their threes, don't they? So let's look first at the thunderstorms. They usually develop in very warm, very moist, unstable air, where that air is going to be lifted quickly over conditions that makes it unstable. Three stages. And first, we mentioned these clouds before. The cumulus stage is associated with convection. Could be because of mountain barriers or a cold front. Something is making the air go up. And as it goes up, it picks up a little bit of spin from the Coriolis effect, counterclockwise spin, and that is the cumulus phase. The mature phase is then, do they have slides that show this better? Yeah, okay. That would be the cumulus phase. That's when it's forming these things. You have the updraft. Around here it's mostly convection, but you could have the mountains contributing to it. Pulling the air up and growing taller and taller, picking up spinning as it goes. At the mature level, what happens, the updraft can no longer support the growing ice crystals, because as this cool air goes up, higher elevation, the air gets cooler and cooler, and ice starts forming. As long as that updraft is strong enough, that carries the ice crystals on up there. But they keep growing. As it gets colder and more moist air comes up, at some point, they get heavy enough, they turn and start falling. Okay? That's mature. The updraft can no longer support the growing ice crystals and snowflakes. The falling frozen water on its way down melts and becomes rain. Now, what happens sometimes is it falls and starts coming down, and then it meets a fresh new updraft and pulls it back up again, and now those ice crystals that were falling now are going back up, getting cold again, and growing bigger. And then go down and repeatedly get picked back up, and finally get so heavy they fall, and if they're falling, they can't all melt before they hit the ground. That's where you get hail. The hail is up there, the ice is up there, but the hail is formed through ice accumulation cycles, several of those, and sometimes it gets heavy enough it hits the ground. And then the final stage, the updrafts are exhausted, and all you have is then the rainfall. Everything is falling out, and your clouds are losing some of their strength. Okay? So that shows the stages of the thunderstorm. And again, three stages. The cumulus, when they start accumulating the moisture, okay, in the big clouds. The mature stage, when it starts dumping on you. And then the final stage, as it just works its way out. Okay. Now, let's talk a little bit. We call them thunderstorms. Guess what? You never have thunder unless you have lightning. You may not see the lightning, but if you hear thunder rumbling somewhere off down there, somewhere there they had lightning. That's the only thing that produces thunder.
What causes it?
Okay, very good question. So let's go back to our big cumulus clouds there. You got the updrafts, the downdrafts, the stuff is moving around like crazy in there, circulating, precipitation. All that activity tends to separate. It's just like walking across that polyester carpeting with your shoes. You're knocking off electrons one way or another, and you're building up charge. Well, the clouds are doing this as they're moving. All those things are moving up and down within the clouds. They build up charge sites. They separate the electrical charges. You have some positive areas, some negative areas. The charges accumulate in different parts of the thunderhead. Okay. And those charges build up. The more activity you have, the more they build. At some point, they build up so much they can't sustain it anymore, and that discharges. So lightning is discharged between the charge centers. Okay, now how do these happen? They can be either cloud to ground lightning. That's the kind we're used to thinking of. The lightning initiates in the cloud and comes to ground. Now, what may be, I think it's a lot less common, and you usually don't realize it's happening because it happens so fast. Actually, the ground could get the negative charges, and it goes to the cloud where it's a positive. And you actually have ground to cloud lightning. Usually lightning is so fast you can't tell where it started, but a few people have been able to take, what do you call it, high-speed film and set it up and take pictures of lightning, and a couple of them have actually hit it just at the right time that they see the spark leaving the ground and heading toward the cloud. Bizarre. Now, if you happen to be on the ground about the time it does that, you could be in for a shock. Okay, put mildly, if you're not toast. But I think before that would happen, you would start feeling the energy in the air, like your hair would start standing up and things like that. I would think that would happen. And then the other kind is cloud to cloud lightning. Okay, one cloud is built up a positive center here, another one a negative center here, leaves a negative and goes to positive. Okay. I remember one night in the Navy, we had watches, standing watches on the bridge, which is not the highest point, but way up there where you can see everything. And it was what they call a dog watch. We had 4-hour watches, and I would start at midnight. Midnight to 4 in the morning, that was called the mid-watch. You lost 4 good hours of sleep there. You might get a little sleep before, maybe a little bit after, but 12 to 4 in the morning. That was one long watch. That was the mid-watch. Then you had the morning watch. It was 4 to 8. And that worked out okay because when you were coming off watch, other people had eaten breakfast already, come and replace you. You go down and catch breakfast afterwards. It works out fine. And then you had 8 to 12. That's the real morning watch. The other was the early morning watch. And then, again, the people coming on to watch each lunch before they do, and the people leaving watch each lunch after they get off watch. Fine. In the Navy, you didn't miss many meals, okay? And then you had the 12 to 4 watch in the afternoon. That worked fine, no problem. But then, when you would have had the 4 to 8 watch in the evening, supper is right in the middle of that. 4 o'clock is too early for supper. 8 o'clock is sort of late for it. Unless you're from Europe, they eat really late over there. So what they would do, they'd split that watch into 2 2-hour watches. So you go and watch for 2 hours, and then someone would eat their supper early, like at 5 to 5:30, come and relieve you. Then you go down and eat yours a little bit late, after 6. And it worked out well. So you called those the dog watch. I don't know why they do a dog 2-hour watches. It was one of those 2-hour watches. I don't remember which was earlier or later. I went up there, and it seemed like maybe it had already started, but it started sometime, maybe after I started on the watch. There were clouds all over the place, and all 2 hours, there was just networks of lightning all over the sky. It was incredible to watch. I thought it's got to play itself out. And maybe we were going right with the front and it was just picking up more energy. No rain. We could stand out on the wings of the ship and watch it. It was just phenomenal. It looked like spider webs of lightning. Hardly any time there wasn't some lightning up there. It's usually multiple bolts, not big ones. And the thunder wasn't really all that loud, but every time there's lightning, it creates thunder. And here's to answer Brian's question. When lightning strikes, wherever, however it does, ground to cloud, cloud to ground, cloud to cloud, however it is, what you have is excess electrons here, negative charges, deficit of electrons here, positive charges, whether that's ground or wherever. And then when the potential gets big enough, then the charges fly from the negative side to the positive side. And it's basically arcing and sparking is what it's doing. And when that happens, the air around it, when that lightning goes through, the temperature varies greatly, real quickly. And when that happens, the air expands very rapidly. And as soon as the lightning passes, it contracts again. Well, that's a pressure wave. Expansion, contraction. A compression, a rarefaction. Okay? That's what makes it up. From the heated air produces a crack of thunder. So that's why you don't now. I've heard people call it heat lightning. It doesn't matter what you call it. It's when one charge here and there. Now sometimes the heat lightning, cloud to cloud, or what they call heat lightning, is cloud to cloud lightning most of the time. And they may not get any rain out of that. It's just motion, but not enough moisture to actually cause rainfall. They say that happens a lot in the Southwest.
You usually don't hear thunder with that.
Well, the thing is, what you see is reflection of it way away. If you were under that, you'd hear the thunder. The sound doesn't travel as far, and certainly not as fast as light does, as the light does, and it probably is dissipated and you just don't hear it. But I guarantee you, if there's lightning, there's going to be thunder. It may not be a huge crack, but you do have thunder. You can't help it, okay? It's going to be there. And here's sort of the picture of that. Because of the motion, all this updrafts and downdrafts are going on in both of these clouds, okay? And if you wind up with an excess of electrons here, a deficit here and here, you can have cloud-to-cloud lightning here. Excess of electrons here, deficit here on the Earth, cloud-to-ground lightning, okay? But over here, where you had a deficit of electrons, if these electrons, if this is attracted electrons here, this is attracted, or the electrons are fled here, left at positive here, then if this gets a big enough potential, it can go up. And this is within a cloud, and this is between clouds. So you have all these combinations going on. So, thought that was a fairly decent illustration they had there. Now let's move to number 2, thunderstorms, and moving up a notch, tornadoes. Now tornadoes are usually smaller than thunderstorms, usually, okay? But they are the most violent weather disturbance. Sure, a hurricane is going to affect a bigger area, and perhaps for a longer time, and there's more energy in it, but for a concentration of energy, nothing beats a tornado. I tell you, it is the smallest and most violent weather disturbance. Rapidly whirling column of air. The diameter can be anywhere from 100 meters, which is basically a football field length, to 400 meters. That would be 4 football fields end to end. That's pretty big. In fact, that's getting pretty close to a quarter of a mile, okay, in diameter. There have been some in the state of Alabama in the last couple of decades that have been bigger than that, close to a mile wide. Those are monsters. Okay. The wind speeds up to 480 kilometers per hour. I'll multiply that by 0.6. that would be about 300 miles an hour. 300 miles an hour. That's devastating. Okay? The damage is reduced mostly by high winds, but you have some by the drop in pressure. In fact, this is characteristic of a tornado. If we were here and one struck, the odds are the windows would blow out because there's such a violent drop in pressure outside, the building is still at the normal pressure inside, the windows usually blow out. Now, you would think that wouldn't be harmful and stuff, and it's not unless you're outside the building, but tree limbs are broken off and thrown into the thing, so you don't always have the glass going out. Sometimes the tree limbs or bricks or whatever are going to bring it in, you know, so that could happen too. So you have that drop in pressure at the center, and the big danger is flying debris. Sometimes these are cars. Okay. Remember the movie, what was it called? Twister?
With Helen Hunt.
Yeah, Helen Hunt. They had cows being blown around in it, didn't they? I'm not sure that you really see that many cows flying around, but it was really a big spectacle.
Like trucks.
I heard the last one was somewhere. A horse was picked up.
Yeah. I mean, it can happen. It surely can.
Well, they didn't hurt him. They didn't kill him.
Right.
They just picked him up in the air.
Yeah. And a lot of times these tornadoes do come out of, like I said before, these intense thunderstorms. Sometimes they come out of hurricanes. And I did want to say this, especially when you have this drop in pressure. I don't know if you ever noticed. What's the most frequent damage from tornadoes?
Wind speed.
Yeah, but I mean, what physical thing do you notice that always seems to happen first? Shingles blow off the house, right? Yeah, that's easy to do. Well, part of the reason for that, but it extends to that, often roofs are taken off the house. And sometimes houses are lifted off their foundation. Sometimes not go very far, just lift it off, twist it a little bit, and set back down, but they're not where they were supposed to be. The reason for that is a drop in pressure. There's less pressure outside, it literally lifts the house off the foundation, or lifts the roof off the house, or in the mildest sense, lifts the shingles off the roof. Because it really does do that. It's such a big drop in pressure. Okay? Here is one picture. Your book has another one. The one in the book is Marquette, Kansas. I think this one was near Dallas, Texas, the one on the slide here. And it seems like I remember reading about it. That one was nearly a mile wide. This one in Kansas looks like it probably wasn't quite that wide, but it sure looks mean, ugly, nasty, and as if it really going to do a lot of damage. Okay. Now, sort of surprised they scooted right past that. Let's look at the tornado damage chart. I thought it was going to be on the slide set, but I don't see it here. So let's take a look at it. Tornadoes are rated on wind speed and damage. Here is a scale of approximate wind speeds. It's just approximate. A Category 0 tornado. Light damage, winds less than 120 kilometers per hour. That's about 75 miles an hour. Folks, that's still going pretty fast. And I'm in the car driving to work or driving home. Generally, I'm right around that speed. If not, it should be a little bit less, but right around that speed. That's moving. It really is. And I think I told you before, Category 0 did hit our farm. At least they said it was Category 0. And I think I told you, my brother was entertaining his oldest daughter's family, a medical doctor. Dan's a farmer. He's an electrical engineer, but works on the farm and also worked for a power company. But, here he had the chief of pediatrics from Ohio State University State Hospital. I mean, that's like our children's hospital magnified, okay? He was head of pediatrics there at Ohio State, and his wife and, of course, his son who was married, and daughter, and I don't know if his sister was there, but, trying to impress him with the farm. And he said, looks like we may get rain later. Let's go out and see the farm now. So he took them out and driving them through, and they were in a cow pasture with cows had been around, and they heard something and looked across the field, and there went Category 0 tornado in our neighbor's field going down, and then turned around to look, the cows had disappeared. They headed for a low area with as much protection as they could get. That tornado, there was a big house on the hill. My older brother and his wife had just moved out of that house because her mom had died and her brother actually inherited the house, but she was a nurse and she was living there as long as her mom was alive to take care of her mom. And then when her mom died, her brother said, okay, I want my house back, So they were kicked out. They had been out about a month or two when the tornado came and did enough damage to that big, old, solid house that they certainly could have repaired it, but it would have been cost effective to repair it. So that was the Category 0, okay? Came across the field, and it cut a swath as wide as this room. Every tree was either damaged or uprooted in that swath. And I think, that's a Category 0, and I mean, that swath is you can still see exactly where that path went. It went up and hooked around my mom's house. My mom was at home alone. She was in her upper 70s at the time, I think. And she heard the noise and went out to check on it. But when she went out, it was passing that way, and all it did was damage a few shingles on her house, ripped limbs, big old limbs out of a magnolia tree not far from the house, wrapped around, pretty much wiped out one farm shed, and what my dad had built as a shop area, hardly a block was left on top of each other. And that was behind the house. It ripped around, basically did a little bit of shingle damage, and also that corner post on the porch was off a little bit, from its foundation. And Mama was out there. Boy, that was some wind. Mama said she was sweeping her porch off. Shut it just after it was making its way on back. Somewhere it must have lifted off and gone on from there. But there was debris they found in a field from houses way down, further upstream from that. And that was a Category 0. Damage to chimneys, tree limbs broken, small trees pushed over, signs are damaged. Category 1. Moderate damage is the winds from 76 to 112 miles per hour. Roofing materials removed, mobile homes and moving automobiles are pushed around or overturned. Category 2. Considerable damage, winds 113 to 155 miles per hour. Basically, roofs are torn off of homes. Mobile homes are usually demolished. Boxcars are overturned. Large trees are snapped and uprooted. Lighter objects become missiles. Okay, that's how they say that. they become missiles. They'll fly through a window and cause a lot of damage. That's why they say get out of rooms with windows. Small, lower interior rooms. And that's only a Category 2. Category 3, severe damage, winds from 156 to 205 miles per hour. Roofs and some walls are torn off houses. Whole trains are overturned. Most trees are uprooted. It's pretty bad. Okay. Category 4, devastating damage. Winds 206 to 260. That's miles per hour. Homes are leveled. Cars are thrown. Large missiles are generated and thrown around. And then the highest. Eyes are giving me fits here. Incredible damage, winds 261 to 318 miles an hour. I don't want to be anywhere close to that, okay? Homes are demolished, swept away, automobile-sized missiles fly through the air more than 100 yards. Trees are actually stripped of their bark, okay? Now, that, what was it, April 2011? That big line of the tornadoes that came through. If I'm not mistaken, there were at any one time sometimes 2 or 3 of those Category 5s on the ground in Alabama. Trying to think, Phil Campbell was a town up in northwestern Alabama, right? If it wasn't the whole town, it was a big plant in the middle of town, just completely wiped out. And there were some others up in the area, I can't think of their names now. Hamilton? No, not Hamilton. Another one, the one that started with H. I mean, just massive damage there. So there were those up there. The one in Tuscaloosa, was that a 4 or 5? It was major though, and there was at least that one, and then I think further south there was probably another one. And the weather people say, hey, you know, we can't track all these. We're going to try to hit the ones that are affecting our area, not the ones in the other parts of the state, and we're just going to hit the big ones because we can't mess with all the little ones. It was a devastating day. To hear Jerry Tracy talk about it, it was a minor time before that I think it may have been the Oak Grove that Jerry was saying this woman was inside doing something and hadn't had her TV on. And I don't know if they had alarm systems back then, or if she hadn't heard it. And the neighbor called her and said, are you still there? And she said, yes. Why? She said, there's tornadoes on the way. I mean, and so she went out and looked and could see one across the field, and it appeared to be heading her way. And she couldn't think what to do that she had time to do. So they had a crawl space with just a small opening in it, and she got almost into the crawl space about the time it hit, just enough she grabbed onto a piling that was under the house, supporting the house, and held onto that for dear life. And she said her shoes were, I think she may have had house slippers on, so sucked off her feet, she never saw them again. She was that close to being caught by that tornado. And she said she was hugging that piling as hard as she could because it was the low pressure was dragging her out, trying to lift her out from there.
Was that 98?
What's that?
Was that 98?
That may have been. That would have been about right.
I worked for a cable company back then.
Uh-huh.
In my area.
Right.
No program.
Uh-huh.
I knew a lot of folks down there.
Yeah.
know, he woke up, the house was tearing up, and it
Wow.
sucked him in the air.
Yeah,
He said it was totally dark, and he was bumping into stuff in the air. So
Wow.
finally knocked him out.
yeah,
He woke up in a field.
yeah. And you hear all sorts of weird stories like, several years before, back when I was probably in junior high school, there had been a small tornado. I don't know if they had the categories back then, 0 or 1, I bet, that went through and took roofs off houses and things like this. And this one place, it was not a well-built house probably to begin with, but it sucked the roof off and did just damage, throwing things around. But on the kitchen table, there had been a vase with a rose in it, and it sat right there. Everything else in the house destroyed, and the rose was sitting in a little vase sitting on the kitchen table, and it wasn't moving. And so weird things happen. And I think that's the one that I heard, that someone found a pine needle sticking out of a power pole. And they say, wow, that pine needle was forced into the power pole. And someone else said, no, take a look. It was on its way out of the power pole. It had gone in the other side and almost made it all the way out. There was that much energy. To think a pine needle, you think would crush it, but it was going so fast, it acted like a track.
There was a lady, when I did her cable, she had an old window on the wall
Yeah.
with pictures. And I saw pictures of the tornado. I'm like, oh, you kept pictures of the tornado damage? She said, I kept this window because this here in one wall was the only thing left.
Oh my goodness.
And we were in the room, and
Yeah.
it tore 3 walls down, and it left the wall that they were sitting by.
Wow.
In the bathroom. That was the only thing in that window.
Right.
She said they had to tear the house down, so she took that window out
Huh.
and it as a frame in the house.
Right.
And I heard about people getting in the bathtubs, and
Yeah.
the bathtubs actually taking it off the landing. Still in.
Oh, that had to be so scary. I mean, just unbelievably scary. It's funny to talk about and hear about them later, but I can imagine being there. I mean, but then too, things happen so fast, but it sometimes will seem like it's taking forever, at the same time, So it's just really, really scary. Okay, so that's tornadoes. Let's move to hurricanes. Now, hurricanes, they don't give a lot in leading into it, but they form in stages and sometimes die in these same stages, okay? Usually they start near the equator. The ones that affect us are on the west side of Africa, and they start there as tropical depression, basically just an area of low pressure, like we described earlier. And those tropical depressions are usually winds moving at about 55 kilometers per hour, which would be 30 to 35 miles per hour, about 35 miles per hour, or less. No big deal. I mean, that's high wind. You don't want to be out there in it too long, but that's a tropical depression. As it continues to build, usually created by heat, then more intense low pressure area. Now here's the thing. This is the main way they measure hurricanes. Not by the wind speed, though they do that, but it's mostly by their pressure. Low pressure for a tropical depression, intensely low pressure, more intense low pressure for a tropical storm. Now you're up to 56 to 120 kilometers per hour, which would be like, what did I say? 30 to 35 miles per hour up to about 70.
It's got 75.
5 miles. Oh yeah, okay. It's in the book. 75 miles per hour. So that is really moving. That's a tropical storm. And then, if it continues to grow, it moves into a hurricane. Very intense, low pressure. Winds in excess of 75 miles an hour, is what you said. Okay? The fully developed hurricane has a very calm eye, and then surrounded that intense rain and thunderstorms surrounding, but the eye itself is just as calm as it can be. That's where the low pressure is really, really, really low. And around that, all the swirling is happening. They have a neat picture in your book, figure 2319. It shows a satellite observing the hurricane's eye in counterclockwise motion. And look at that eye right there in the center, and then look how big and broad the area is around that. Now, I don't know where they took that shot from, but that is quite a shot. I don't know if that was a space shuttle or something like that. I don't know. Now, there is an overhead shot of an eye, okay? And you can see there in that center, if you were there, it would feel like just a perfectly calm day. Look around you, and nothing is calm. You know, sometimes the eye can be quite wide, but you can still see the walls of it, and the wind is blowing like crazy, and yet it's just as calm as it can be. That Oak Grove tornado back in 98, when the alarm went off, it was around 5 to 5:30, maybe 6 o'clock in the evening, seems like. And I was in here teaching a Math 098 class, I think it was. It was the earliest evening class, and I had a pretty good room of students, and I heard the alarm go off, and I thought, this is a strange time to be testing. But I looked out at those trees, and it was, all of them were fully leaves like now. Not a leaf, not a branch was moving. It was as still. I said, this is still as it can be out there. I mean, not a leaf was moving. You see, even now, there's wind blowing branches around. Nothing was moving. I thought, that must be a fluke. Okay? I went on teaching, and I can't remember his name now. He was the night coordinator. He stuck his head in the door in about 5 or 10 minutes and said, get downstairs. There is a major tornado in the area. And I said, there's hardly a leaf. He said, it is. So we went downstairs and waited. When I got home to talk with Karen, she said it was the same way there. Like I said, the airport, which is less than 5 miles from us, it was just before it got to the airport, it was deadly. And she said hardly a leaf was moving in our yard. What it is, all the energy from the area was sucked up to that place where the tornado was. It was the same type thing here. All the energy is sucked up into that surrounding. Now, I had a friend when I was at grad school at the University of Georgia. He was an undergrad student. He had started in forestry. He was sort of an outdoors type person. His dad was a pilot for, I think, Eastern Airline. And Doug had, he liked flying, but he also liked being outside and stuff like this. So he got his forestry degree, but there weren't really great jobs then. It was sort of a down period economically. And he decided he wanted to fly too. That was good income, he liked to fly. So he went back and started picking up his pilot's credentialing. And the airports were pretty well booked then, so he was new and didn't have that many flight hours. So people much more senior to him were getting the jobs there. So the job he took was with NOAA. Anyone know what NOAA is? Oceanic and Atmospheric Administration. Very good. He got a job with NOAA, and his job was to fly planes, all instrumented, and he had the scientists and other people on board in the plane, to fly the planes over the hurricanes and drop down into the eye and take all the measurements there. Okay? So it's big enough for a plane to get around in there. And that's what he did during these storms. He was a hurricane pilot, and he flew over the hurricane, which was probably pretty rough and bouncy ride then, but got into the eye and flew down. They took measurements at different elevations. And when they got everything they needed, they'd fly back out. And that's how they knew what the pressures were in those things, because you have people doing that. All right, here's the picture of what's happening. Now this is a cutaway view, okay? It's a lot like the big thunderstorm, only bigger, okay? Bigger in sense here. The eye is the place in the middle, and like I said, it's low pressure, so it's sucking the wind down into the low pressure, trying to equilibrate that, and that air that's pulled in, this is in the tropics, so that is already warm, moist air anyway, pulled down, it heats up when it goes up, and then it goes back up, and in its flight upward, because of the Coriolis effect, it creates the twisting force, and that's why you get the counterclockwise motion. Now this is an idealized account, but it's showing that I as being about, would you say that's about 15 kilometers on either side of zero, so about 30 kilometers wide, which would be about 18 miles wide. 18 miles of calm in the middle of that thing. And then the storm, from that 15 kilometers to about 80 kilometers, you don't want to be in that area. So 15 to 80 would be 65. So that would be about 40 miles on either side. So a diameter of about 80 miles or bigger. And you have the maximum winds and rains are just outside the wall to the outside. You still have hurricane force winds for at least 40 kilometers, which would be 24, 25 miles. And then you have what we call gale force winds on the outside of that. But these things are moving, and so even though you're outside of it now, you may not continue. Intense rainfall in that, but then it's sucking up energy as it goes, so they don't necessarily weaken that much. Now, I can remember Ivan. I don't remember what year it was, but we had moved into the house where we currently live now, and we knew Ivan was coming. They had been tracking it. And where did it cross in? Somewhere around Gulf Shores, or somewhere close of Alabama, or very close to it, and came up. And Ivan made it. And how far is it from Gulf Coast to here? Someone said about, is it 400 miles, 500?
It's, we went from the Gulf Shore.
Yeah.
Maybe probably
300 miles, okay. And 300 miles over land, by the time Ivan got to Birmingham, it was still a tropical storm, strength. You still had winds in that area. It was pretty fierce. We lost power, of course. We were in a wooded area, and a tree went down on a power line just up the hill from us. And we were out of power. However, it was pleasant weather. It was summertime. So we weren't stifling, but we had gas range top, so we were able to eat fine. We just did everything on the gas stove top. We couldn't use our oven, of course. Friends of ours came up from what is the island off Mobile? Is it Sapelo Island, or is that over in Georgia? One of those islands. Second, Dolphin Island. That's it, Dolphin Island. Dolphin Island. She was working for the Food and Drug Administration or somebody down there, and they said, "You better get out of here." So she knew we were in Birmingham. She called. We said, "Yeah, come on." She actually brought a friend of hers who didn't have anywhere to go. So they came up, and about the time they got there, after they'd been gotten there about a half hour, 45 minutes, the power went off, so they were without power with us too. But we had a good time. Some trees in our yard lost some limbs, but nothing really all that major. Other places in the neighborhood, a little bit worse off than that. Lots of people without power for a while. She got back down to Dolphin Island later, and she said, they didn't lose power down there. So she came all the way to Birmingham to lose power. And she said, really, they didn't have much damage there either, and they were just very, very lucky. Okay, hard to predict. So let's talk about weather forecasting, talking about hard to predict. Weather forecasting is based on mathematical models of the atmosphere. But when you think about it, our atmosphere is an enormous volume of stuff, okay? It starts at ground level and goes hundreds of miles in the air and goes all around the globe. So we're basing mathematical models on the atmosphere. It takes billions of calculations to necessitate the use of supercomputers. Before they had supercomputers, they weren't able to do this. They could look at conditions and predict and say, we think this probably will happen. Now they can actually run these models, and you hear James Spann and Jerry Tracy and stuff, well, the RPM model, this model, that model, there's all these different models out there. Well, some of them are saying this is going to happen, others are saying this is going to happen. Well, yeah, we're a little better off because we take the best guess of what they say. They're fairly accurate forecasts up to about 3 days. And that's it, folks. You see the 7-day forecast? That's a guess. Okay? The 3 days, next day is pretty good. Day after that is reasonably good. The third day out is fair. Anything beyond that is really a guess. But the deal is, you see, before you get there, they have a new 7-day, and what they were guessing 7 days, now it's 5 days away. They have a much better idea. Still probably wrong, but a much better idea. By the time we get to 3 days, you've forgotten what it was 4 days ago, how far off they were, It doesn't matter. But they do a pretty good job. The major uncertainty is the insufficient technology to connect the small and large-scale events. You know what they're basing it on? They send up a weather balloon, I think about 3 times a week, and I'm guessing they do one out of the Birmingham area, the Huntsville area, maybe Montgomery area, maybe Mobile area. So maybe 4 across the state of Alabama. The weather balloons are going up, picking up temperatures as they go up, wind speeds as they go up, moisture levels as they go up. That's what they got to model the whole state on. You can't get a great model out of such, and that's only a few days a week, okay? So no wonder they have difficulty connecting that. Now, sure, airplanes flying around, they pick up data and send it to NOAA and everyone. That's why there's billions of calculations have to be made. But man, ultimately, it's the oceanic influences need to be better understood. And that is sort of a sad thing. I've heard it said several different ways. I heard this recently. I think this is what the statement was. We know more about the surface of the moon and the surface of Mars than we know about our oceans. That's sort of strange, isn't it? But we've sent spacecraft up there. They've got rovers. They've collected materials. They've done all this stuff. Men have landed on the moon, brought back samples. We have a fairly good understanding of those, but there's some parts of the ocean nobody has ever even been there. And we don't understand beans about some of the oceanic influences. Okay? Yeah, we need to know that a little bit better. All right, that ends. Oh, and by the way, before we leave hurricanes, and we should have done it here, hurricane damage, there's 5 categories of hurricanes. Remember we had tropical depression, tropical storm, hurricane. But within hurricanes, there's 5 categories. Now, tornadoes had 6, 0 through 5. Hurricanes have 5, 1 through 5. They're number 1, minimal damage, that's 75, and this is where you're reading that, 75 to 95 miles per hour. That basically is about like a category 0 tornado. Category 1 hurricane. Yeah, about the same. Okay. Moderate, 96 to 110 miles per hour. That's sort of like, that's their category 2, tornadoes category 1. Extensive, 111 to 130 miles per hour, that's about a Category 2 tornado. That's a Category 3 hurricane. Category 4 hurricane, extreme, 131 to 155 miles per hour. That's an upper level Category 2 tornado, and that's Category 4 hurricane. Catastrophic, Category 5, over 150 miles per hour, that's just beginning a Category 3 tornado. And then you've got Category 4 and Category 5 tornadoes, which are much stronger than Category 5 hurricane. Doesn't cover as much area. It's a very small area compared to a hurricane. Hurricane can cover counties. A tornado hits a swath of about a mile, no more than a mile wide, usually. Usually much less than that. Okay? So you see, yeah, tornadoes are much more compact and much more intense where they're hitting, but they don't cover as much area. Okay. Now, the first half of the book, weather. The second half, of the chapter, is climate. Now, the strange thing is, they put weather forecasting and climate together. I would have thought weather would have been weather forecasting with weather, but it's part of the climate. So here we're in the second half. We have weather and climate. You would need to take a break. I've been going for a long time. Let's do a timeout here. And okay.
I was surprised I did as well as I did, honestly.
Oh, what?
When I took your class in
Oh.
112, I was surprised I did as well as I did. I didn't think I'd do that well when I took it.
Well, you had a push over for an instructor. You didn't teach him. All right. Let's look at climate. I think early on, I believe it was probably Ricky gave us a good definition. I don't know which one he did. Weather is what's happening now. Climate is the long haul. I don't know. Maybe one of the others I said. So let's look at the long haul. Climate is a composite, larger weather patterns occurring over a number of years, number of decades, number of centuries, possibly millennia, maybe. Okay. The determining factor, climate is the determining factor of the types of plants and animals at a given location, the types of houses built, lifestyles of the people who live there. Let's think of some of those things, okay? For instance, when I lived in Nebraska doing my graduate work up there, I can remember, what's that? No, they do, but oh, good. And Minnesota has mosquitoes like crazy.
I thought up north they didn't have mosquitoes or fleas.
No, they do. Maybe not. They don't bother you for as long a time, but they do. Minnesota is. I think mosquitoes is a state bird up there. I mean, it's just they got so many. It's the land of 1,000 lakes, and they breed mosquitoes. In the wintertime, you think they all get killed, but somehow they come back every spring. So I don't know how. But the fleas aren't as bad, because the ground gets frozen and stuff. But for instance, I can remember seeing one pecan tree of all the time I was in Nebraska, and it was really freaky that neighborhood had a pecan tree. There must have been another around to pollinate it. But pecans just don't do. They need a longer growing season than they get there. And I also remember when you never saw armadillos in Alabama. They were always down in Texas, real near Mexico. Now, I can remember when I was in Nebraska, people started talking about sighting armadillos for the first time in their lives. Okay, so yeah. That determines the types of plants or animals in a given location. Types of houses built. What do we mean by that? Especially think here. Look around this campus. What's common to just about every building on this campus? I can think of one exception to it. That was a rehab. Every one of the buildings here have flat roofs. Now, I don't think that's the best design for a building, but look at it. Every building on this campus is flat roof, except Jess Lanier building, they got a rehab a few years ago with the metal roof on the slant. Problems with flat roofs, well, they're supposed to tar them down really well and seal them well, but water still stands, and if water stands, it's going to make its way in somehow. So far, there's not as much leakage as I would have thought with these older buildings. So, but you see, flat roofs are cheaper than shingles, and angled roof. But angled roof helps. Do you think you find many flat roofs buildings in Grenoble, France, say? Or I'm trying to think of places that have Winter Olympics. No, where you have a lot of snowfall, you do not want to have a flat roof, okay? Because you're going to cave it in, because the snow just accumulates on it. And the more snow you get, the steeper the roofs get, okay? You don't even want a roof that has this kind of pitch to it, where there's lots of snow. You're going to cave it in. The more snow you get, the steeper the roofs go. Also, you want houses with a lot better insulation if you live in Minnesota than if you live in some areas that are not nearly so cold. Lifestyles. Everybody in Canada plays hockey, okay? Nobody in Alabama plays hockey much except around Huntsville. I think they have a team or league up there maybe.
It's coming back.
It is, yeah, it really is. But most of your good swimmers are from California and Florida and places like that. Yeah, you have good swimmers from other areas, but you just, middle of winter, you don't feel like going out and going swimming, in other areas, okay? And that's why, a lot of your great football teams are in the Southeast and the Southwest, because here we can practice all year long. In the North, they just can't, okay? They can do some stuff inside and stuff, but so lifestyles vary. Climate is a determining factor in lifestyles. Climate influences the shape of a landscape. We talked about that earlier too. The types of soil. Why would it influence the type of soil? Okay, that's certainly true. The agricultural type and productivity, that's big too. We'll get to that. Let's do types of soil though. Remember my 10-degree rule that I told you before? Most chemical activity in the soil and biological activity in the soil, of course they go hand in glove. For every 10 degrees you go up, above 40 degrees, you double the chemical activity. And then they go up another 10, you double that. So you're 4 times as much. Another 10, you're 8 times as much. So yeah, here in the Southeast we have chemical weathering of soil particles like the humus, the organic material and stuff like that. That's happening of course it's happening right now, but it would happen in January. In Minnesota, there is none of that happening in January. Whatever is there when the first snow falls or when the land gets frozen, it stays pretty much like that until it falls out in the spring. We have weathering going on all the time. So our soils are very highly weathered soils, and up north you have soils that are much deeper, richer, and not nearly as weathered as ours. Now, Brian was mentioning agricultural type and productivity. Those rich soils in the Midwest, they can grow a lot more soybeans and corn per acre than we can. But guess what they can't do? They can't double crop. We will plant wheat in the wintertime. We harvest that in May, and if you wanted to, you can follow it up with corn or soybeans. You get 2 crops out of one field. You won't get the production they do up there, but they only get one. And guess what? If they have a late spring, they may not get that one crop in. If they can't get into the field on time, then they plant the crop, it may not mature before that first frost. And then they're hurting badly because they pour all that money into the production and don't get anything out of it. So agricultural type of production for sure. Beef cattle. A lot of the breeds that I grew up around, Herefords, Guernseys, Holsteins, you know, those are northern breeds.
What you said, Hereford?
Hereford is a beef cattle.
Oh yeah.
Okay? But a Santa Gertrudis and a Brahma, those are hot weather breeds. Those are Southwest. They're also meaner than snakes. Okay, the Brahman anyway. But yeah, types of productivity for sure. We can do poultry production like crazy down here. Kind of hard to do in Minnesota. Keep those birds from freezing. That you have to really be eating those areas. We do a lot of things down here they can't do there. They have much richer soils than we have here. Yeah, agricultural type of production that changes. Let's look at some of the major climate groups. Two primary factors. The intensity of the incoming solar radiation, for sure, is determined by the angle of incidence. Near the North and South poles, even in the dead of summer, the angle is very low. And a lot of that gets reflected off. You just don't get a lot of warming there. Around the equator, the angle is very, almost 90 degrees, almost all year round. You get an enormous amount of solar radiation there. That determines the number of daylight hours, okay? On average, we all get the same number of daylight hours. Just at the North Pole, they get 24 hours of daylight. Not very bright daylight, but daylight for the summer, right around the summer solstice, and 24 hours of darkness in the winter solstice. It all averages out, except how many are in a row and how bright is that sun. So those are the primary factors. These are mostly called, both of these, by the tilt of the rotation axis. How much is that? 23.5 degrees, you got it. The equatorial regions receive more solar radiation all year round. Anywhere inside the tropics, Tropic Capricorn, Tropic Cancer, 23 south, 23.5 north, you know, that's your large amounts of solar radiation. The intensity changes on a yearly basis, especially in the temperate regions, like where we live. Right now we're getting pretty intense solar radiation. It gets hot out there, okay? The intensity changes. Come this time, come January, not going to get as much intense radiation, and it won't last as long, okay? The number of daylight hours varies annually. I think they mean over a year, okay? Right now we're getting probably close to 13 or 14 hours of daylight a day. In the wintertime, it will be 9 or 10, okay? It varies over time, okay, during the year. Now, let's look at climate and latitude. That's the biggie here. The low latitudes, what they mean are small number latitudes, not low as in near the ground, but low latitude have high solar radiation. Yearly variation is very small. The temperatures are uniformly warm, okay? And that would be in the tropics, right around the equator, and pretty much between Tropic of Capricorn in the south, Tropic of Cancer in the north, 23.5 degrees south to 23.5 degrees north. Those are called low latitudes. You got high intense solar radiation. See, the sun shining on it is almost direct, okay? Yearly variation in temperature is very small. In fact, Hawaii is right in here somewhere, and it's usually between 72 and 80 degrees all year round. Okay, is a high temperature or average temperature all year round. Okay, and a lot of times near the equator, that's what you get. Yearly variation is small, the temperatures are uniformly high. In the middle latitudes, which are between Tropic of Cancer and the Arctic Circle, Tropic of Capricorn and the Antarctic Circle, here the higher solar radiation during the summer part of the year, okay, lower during the winter part of the year. Overall, the temperatures are lower than they are around the tropics, but greater variation than in low latitudes. In fact, our summer days, we may be warmer than it is in Hawaii, but on average, we're cooler, okay, than Hawaii, because Hawaii never gets anywhere closer to the cold as we do, okay? So we have overall temperatures, the temperatures are lower, average is lower, but you have greater variation. You have some days you're actually warmer, and some days you're frigidly colder. And then the high latitudes, that's from 66.5 degrees to 90 north and south, okay, inside the Arctic Circle or Antarctic Circle, the maximum amount of radiation during one part of the year, and even though it's maximum, it's at a very slanting angle, so a lot of it gets deflected anyway, but the other half of the year you get absolutely no solar radiation. Okay. Overall, the temperatures are the very lowest and with the widest variation. Now, they won't ever get up to 90, okay, so they don't get variation on the high side, but their variation on the low side gets really, really, really low, okay? So they can go from minus 73 to positive 40 or something like that. We don't get anywhere close to that, you know. We get, say, 100 to 0 to 100 would be about the best we could do. I don't think we hardly ever get 0 and very seldom get 100. But that would be our greatest variation, where they could be minus 70 or 80 up to plus 40 or 50 or even maybe some 60s. Great deal more variation, but everything's cold. Okay. Make sense? So this leads to climate zones. Okay? We've almost the same words here. Defined in terms of the yearly average temperature averages. The tropical climate zone near the equator receives the most solar radiation. Basically, it's hot. Year-round hot. Okay? That would be in here. Now notice these are not strictly inside the Tropic of Capricorn and Tropic of Cancer. Some is above, some is below, you know, all in here. A lot of variation here. Land masses change things a little bit, but that's generally it. The polar climate zone, they go to the extremes now, and this makes it look much bigger, but you remember it's really a small globe. I mean, a globe didn't really get small at the top. This has been spread out a lot. But that's the least solar radiation and cold year-round, but just sometimes we're much colder than other times. The constant daylight in part of the summer, constant darkness in part of the winter. And then the temperate climate regions, that's where we live, okay? Intermediate between the other two. Now, then they throw this in here. This has really, it seems out of place here, but it's so true. Rainfall patterns shift seasonally, okay? Sometimes they shift rather strangely too, like this summer. Knock on wood, I'm not complaining, but I've never seen this much rain in the summertime. It just, I mean.
Well, we usually have, you know, to suffer from droughts.
Yeah, exactly. And I mean, I can think of many end of Julys when the trees just look sad. They've already started dropping leaves because they can't support that many. In the spring, they had plenty of water, they grew them, but then by this time of year, they're falling off brown. Not changing color, it's just they can't support that many leaves. I don't see any of them. I mean, all those leaves look happy to me. You know, they're none of them stressful looking, and they don't look sad. They look pretty happy. I mean, this is the green you would expect in late spring, really is good. But there's some parts of the world, I know friends we have from India, they talk about monsoon seasons. I have a friend who's in Ghana, okay, he's a missionary over there. And he said they don't talk about winter, spring, fall, and summer. They talk about rainy season and dry season. That's what's because see, all the temperature is about the same here. Who cares what month it is or anything else, except is it dry or is it wet? Okay, that's what they determine their seasons by, basically. It's still called fall, spring, summer, but it doesn't matter. All the temperatures are about the same, but they're dry seasons and wet seasons. So that's sort of why they stuck that in there, I think. Okay? Now this I find to be a bizarre, and this is the rainfall patterns. That's what this one is. Should be down here. This is so strange the way they did it. Come on, at least have curvy lines. But this makes it look like it's very wet here, but then very wet here, as if this can't be wet here and it's wet there. And this can't be wet here and wet there. I mean, it's not that abrupt, and it's certainly not that abrupt, or that abrupt, or this abrupt. There's not too much abruptness there. It's more gradual, definitely more gradual, okay? And look at lucky us. Look at lucky us. Our entire country pretty much is in wet area. Not very wet and not dry. Poor old Mexico, just south of us, they're dry. Okay, they're just uniformly dry. The Yucatan Peninsula is about the only place that really gets lots of rainfall. I mean, they get some, they get enough, but we're just saturated with it. Now, this little portion right here that says dry, that's where the farm is in Georgia. They never seem to get the rainfall we get in Alabama. When a weather system comes across here from west to east, it hits the Appalachians and go north. Okay, and these waves, they say, "Oh, the rain's coming," they'll turn and go north, and they won't get it. So that's part of the reason there's a little bit. But again, this is not accurate. This is just someone's pictorial representation of it. Okay, this is where most of the hurricanes and typhoons and stuff initiate in these hot, wet areas there. Lots of good agriculture here. Then it jumps up in Europe, has pretty good agriculture. But parts of the Soviet Union, very cold, somewhat dry. We are so lucky. Big swaths of South America, fairly dry, some part very wet. Only a little bit of it is just reasonably wet. And that gets to be pretty cold. So yeah, rainfall. And that's basically, you're talking temperatures, rainfall, or moisture. Those two things are the things that determine so much. Regional climate influences. 4 major factors on these regional climate influences. We looked at the big scale, now we're getting smaller scale. Altitude. Now what do we mean by that? How high you are above sea level, basically. Okay? Now, the higher altitude air radiates more energy into space because there's less atmosphere in high altitudes. So the atmosphere acts like a blanket kind of, and the less you have, the more escape. Even though it gets a lot of direct radiation, but it escapes pretty quickly too. So how high you are above, and we are not that far above sea level. Mountains, even though you're in an area that might be sort of low, if you have a mountain there, then that changes everything. Cooler air at higher altitudes. And here's something. The upwind slopes tend to receive more precipitation, the downwind slopes less. Because the upwind slopes, usually the winds are coming off the oceans, and when they do, they've got lots of moisture in them. But when they hit mountains and go up, the mountain is cooling off up there, so it comes off. It's snow, it's rain on this side. And by the time it crests and go over, there's not as much moisture in the air anymore, so the downwind slopes are less precipitation. So usually the upwind slopes are wet, downwind slopes are drier. Okay? Now, it seems like there's some place in the book that says the western slopes have more and the eastern slopes are less. Well, that's true in the temperate areas, but wouldn't be true necessarily in the tropical areas. And who knows about the polar areas, you know, they have really weird weather up there. So I like this one, upwind and downwind. That's far more accurate and precise. Okay, the next two are large bodies of water. Okay? I think I've said this a few times, and I'll say it again. Thank you, Gulf of Mexico, okay? Because if it weren't for the Gulf of Mexico, we would be pretty dry, okay? Because all that moisture had been lost before it came across all that U.S. to get here, but because we have the Gulf of Mexico pumping all this, there's a warm bathtub down there. It has always moist, sending up the thing, so that's why we stay wet, okay? Now, the other thing is that water has about the highest specific heat of any naturally occurring substance out there. I think helium is a little bit more. Helium is pretty rare, okay? And it's a gas anyway. But water has a high specific heat, so therefore in the winter time, if you're near a large body of water, you tend to be a little warmer because that water hangs on to its heat longer. But in the summertime, you tend to feel a little cooler because the water absorbs the heat, absorbs more of the heat, and is slower to warm up in the early season. So that is because of the high specific heat of water. It moderates the temperature change. And we talked about this, I think, in the last chapter. Driving down in the summer to the beach, you go south and you get hotter and hotter, just gradually. Montgomery always seems hotter than we are here. You keep on going down, you get into the county or two above the Gulf. Man, sometimes it's sweltering down there. As soon as you go right onto the Gulf, it seems like it cools off. Because the Gulf of Mexico, the water there has a higher specific heat, and it keeps it more moderate. In the nighttime times, it'll get cooler up in Montgomery, not by much, but a little bit, but it'll stay almost the same temperature of the water because it moderates the temperature change. And then in the wintertime, it's warmer down there, cooler. And the fourth big factor is ocean currents. Okay? And again, we're pretty lucky there. I don't know if we're going to show a slide on this one. Yeah, here they are. Again, we're so lucky because looky here, we get these warm water coming off, tropical waters off the Atlantic. The currents bring it in, up the Caribbean, and then it gets in the Gulf of Mexico and it almost gets trapped there. The Gulf of Mexico is like warm bath water sometimes. I mean, it's just this nice, pleasant, warm thing. And even then, when it moves up, this is called the Gulf Stream. And it moves up and keeps almost all of the eastern seaboard free of ice. Maybe up in Maine, they ice up some of the harbors, but most of the eastern seaboard, nice, and all the ports here can do business all year long. We're very lucky that way. Poor Canada, though, they have the Labrador currents that are very cold coming from Arctic water, and that freezes up the St. Lawrence Seaway and other areas here, so they can't do as much seaborne transportation and trade and stuff. Our coasts are just wide open all year long. Even on the west coast, though, you have cooler air coming in on the Pacific, cooler water coming in and moving south. And San Diego, most of the time when you go to the beach in San Diego, you'll see people in wetsuits because the water is just not really all that warm. And it's way further south than Atlantic City. In Atlantic City and Long Island, they're going to be out there, they don't have wetsuits on, but it's pretty warm there. because the Gulf Stream keeps this warm, the Pacific currents keep that cool. Now, Alaska's kind of lucky, and actually Western Canada is sort of lucky too. The currents that come in here, these are cool for this land temperature, but they're warm for this land temperature. So they're warmer up there. Vancouver is an open port year-round. Even though it's further north, or basically about as far north as it is over here, the Labrador current will actually freeze these waters, but the Pacific current keeps out in Florida, even up to Alaska. Now, some up in here, of course, it gets cold, but on this part of Alaska, Juneau, they'll stay pretty much ice-free most of the year, and they're way up north. Now, up above the Arctic Circle, no, it's going to freeze like crazy. In fact, anywhere in the Bering Sea will freeze like crazy. Okay, so the ocean currents also make big differences, and again, we luck out big time. Describing climate, kind of tough. And this is what I didn't like about that previous slide. The problems are, there are no sharp boundaries. That slide back there that showed, no, that doesn't happen. There's no sharp boundaries, and the boundaries aren't fixed anyway. Year to year, decade to decade, they may waver and change. If you followed much about Africa, the Sahara Desert seems to be creeping south. Places in, they call it sub-Saharan Africa, used to be pretty good climates. They're drier now than they were a decade or two ago. For some reason, the Sahara wants to grow. So there are no sharp boundaries. No two places have exactly the same climate. Now, there are some similarities. The San Francisco Bay Area, north of there, what's that county called? Marin County. Yeah, Marin County. Great, great country. Okay, great place for California wines. Okay, that's very similar to the Mediterranean climate of Italy and France. Great wine growing country there. So they'll be fairly similar, but they're not exactly the same. Okay? A description of the North American climate zone follows, and this is a really interesting description. Okay? And I see a picture here I wish I had talked about earlier. One of the enormous features of the North American continent is the Great Plains. The eastern seaboard used to be totally wooded. Totally. I mean, right here where we are was probably dense forest. Okay? Just about continuously. The West Coast, giant sequoias and, redwoods and things like that, the firs and things like that. But in the middle of the country, flat, grass in the Great Plains. And that's supported, and that's partly because of climate, okay? But it's also because, there are other features in there, but think about how that changed the wildlife. The East Coast, you had bears and mountain lions and things. In the West Coast, you had different kinds of animals, more grizzlies than you did in the East. You had all these things. But in the middle, great herds of buffalo. They couldn't have existed east or west. They had to be there. Now, unfortunately, we went through and killed as many as we could and almost wiped out that. Just incredible. When you read stories of those herds that used to just roam the Midwest, and now you just have to almost go to special areas to see a single little group of them. Okay, amazing. Okay, too much of that. Okay. So here are the climate zones. The feature of the table is pretty much your table 23.1. Then the map of it is this, okay? Now, your 23.1 is a lot more detailed than this figure shows. I wish we had your 23.1 where this was, but we're going to get most of them. And they're not quite in the same order. We'll fill them into place. Okay, the climate zones. Near the oceans, okay, these are marine climates, or near the ocean. Okay, you typically have a fair amount of moisture there. So on the west coast, again, San Diego, not, because you have cooler waters coming down. They don't give off moisture the way that warmer waters do. But from Northern California up to Oregon, Washington, Seattle, Vancouver, this pretty wet. These are marine climates here, okay? Near the ocean, these are your marine climates. As I said, Mexico, except for the Yucatan Peninsula, is a bit on the dry side. The Yucatan Peninsula is also a marine climate. Even though that other map showed it in the dry region, that's not really all that dry. Okay? The marine climate is influenced by the air masses from the oceans. Okay? Then you have continental climates. These are far from the ocean and influenced mostly by the air masses from large land areas. So let's look at a few of those. And again, I wish we had the table 23.1. So I'm going to do a little bit of jumping back and forth on that. Other classifications: arid, meaning very dry; semi-arid, not quite as dry; humid, pretty moist, and on. Okay? So let's start where this starts, the polar. Up here, and you have it around Antarctica too, that's just cold. You're going to have ice on the ground most of the year. It's just cold, just really cold. Okay? Then we have the humid continental, I can't read that word. Subarctic. Okay, that's what it says, subarctic. Now I see it. And that's this area here. Now, you'll notice here that most of Alaska is considered humid. There's some polar and there's some marine, but it's mostly pretty humid, but it's subarctic humid. Okay? Yeah, they have plenty of moisture, but it's really, really cold. And so much of Canada is in that. Okay? Not all of it, so much of it. A lot of it's in the polar, but this is subarctic, humid subarctic. Then you have humid continental, and that was also a humid continental, but what does this say? Mid-latitude. So that's this color, okay? That's where the Great Lakes are. So this is right near the border of Canada and the U.S., right around here. This is southern Canada, this is northern U.S., okay? And it's humid, but mid-latitude, okay? Then we have humid continental, low latitudes. I wouldn't count those very low, but that is a big swath of your farming belt. And this probably goes from, I'm guessing, Pennsylvania in here, across Iowa, Illinois, Indiana, and on west. I don't know how far it includes there. It seems like they're pushing it a bit further west than I would have guessed, but maybe that's true. And then we have the humid subtropical. That's where we live, okay? Humid subtropical. And that's plenty of moisture just about year-round. Usually not as much in the summer when we really need it. This summer we've had plenty, okay? And then we have tropical wet. Okay? Now, I said it wrong. This was the marine, this is tropical wet. Okay? That's a little bit different color. I didn't notice there were two blues here. And then we have tropical. Say again?
Seasonally wet dry.
Okay.
With seasonally wet dry.
Seasonally wet dry, is that what it says?
Yes.
I see dry. How do they phrase that though? Whoa, with seasonally wet dry. Okay, I got it. Hard to see here. Okay, the focus is not good. That's down here. We don't have too much of that. Southern tip of Florida, yes. Tropical with seasonally wet dry. Cuba, this is Hispaniola, I think, is the island that has Haiti and Dominican Republic on it. That's Puerto Rico. I don't remember what island that is. And then the lower parts of Mexico and much of Central America is this tropical with seasonal wet dry. Then you have the semi-arid. And this is the western part of our Great Plains, and that's one reason it is the Great Plains. Then you get desert, okay? This is the desert. They call it desert southwest. Look at how much of Mexico is desert. Now, this is the part that just almost blows my mind. The Yucatan Peninsula. Look at this thing. It's surrounded by water and it's a desert. And you think, how can that be? Well, again, you've got the Pacific currents, colder water up here. They come down here. They don't give off much moisture for the Yucatan Peninsula, okay? And on the other side, this is the Bay of California, I think it is. And water everywhere, but not any to get on the land. And here is the Mojave Desert, and I'm not sure all the deserts in Mexico. There's a lot of Mexico is pretty much that. And then the marine, that was this one here. No, I'm sorry, marine was this one here. And then the Mediterranean, that's it here. That's the wine country, and it actually extends down. A lot of California is what they call Mediterranean. Reasonable temperatures, sometimes not too hot, and the desert gets quite hot, but pretty reasonable temperatures, but not super lot of rainfall, but, well, not really enough. They do a lot of irrigation. That's the big agricultural portion of California. And then the highlands. These are your mountain ranges. These are the Sierra Nevadas, I think, here, Cascades here, the Rockies here. And then you have another high range here and here. Notice the Appalachians don't even count. Okay, they don't even include those as highlands at all, even though they do get into that kind of stuff. Now, this almost, except for those mountains, and that explains a lot of it, it almost doesn't make sense because most of your prevalent wind here is from the west. You would think this would be the wet half of the country, and that would be the dry half. The Gulf of Mexico ensures otherwise. That pumps the moisture up here. That's what keeps all this in the humid region. This gets really wet, but the mountain ranges here block all the moisture from going in. So the upwind slopes of the mountain are wet, the downwind slopes are dry, so that keeps the rest of the country wet, dry, and the Gulf of Mexico pumps moisture up in here like crazy, and that keeps us wet. We're pretty fortunate where we live. Okay? Arid would be the desert type region. Semi-arid would be these kind of regions. Humid would be these kind of regions. Humid, subtropical, I love maps like this that show that kind of stuff. As you can tell, I talk too much about it. Okay. there's an example here, 23.3. The following table lists the average monthly temperature data and total monthly precipitation data for a location in North America. In which major climate zone is this located? Take a look at those temperatures and I'll tell you, it's not the southeast at all. We never get down in the minus degrees Celsius, especially on average for a month, ever, okay? So this is considerably north of us. Now, notice that in those very cold months, you hardly get any precipitation, and in the warmer months, and these are not all that warm, I mean, 7 degrees Celsius is basically 48 to 50 degrees Fahrenheit. That's not all that hot. So you must be pretty far north, and I'm going to guess that would be your humid continental subarctic. Let's see what they say. Ah, that's even colder. It's a polar climate. I thought it was one just south of there. That's polar. For those kind of cold temperatures, that's polar. Okay, I should have known that. Okay, following table lists average monthly temperature data and total monthly precipitation for a city in North America. In which major climate zone would this be located? And again, the temperatures, average temperature, not below freezing. Now, 4.2 degrees would be that's 40 degrees in the February, average 40 degrees. Okay, precipitation, pretty good amount of precipitation there, and that they say is humid subtropical. I can agree with that. It'd be down in our area. Okay. Local climates. This is on page 594 and following. Now you can get really, really local, and that can be called a microclimate. That's a local pattern in the climate. Very, very local. You could be talking about the north side of a tree versus the south side of a tree. That's a microclimate. You do get changes there. The types of moss that grow change on the north side, south side. The types of lichens and stuff. Now that's really micro, okay? They're talking things a little bit bigger, but local climates can be associated with large cities. We talked about the heat island effect. There's another blurb here, concepts applied. Cities change the weather. Now we're in the climate portion, but they're talking about weather. And this is called the heat island or heat dome effect. Birmingham is just about always warmer than it is outside. Now, we live in Birmingham, and when I drive in, I go through Malfunction Junction, get on Red Mountain Expressway, go south there, and get off and go into Forest Park. It's still in the 80s. Remember I was talking about still in the 80s when I got into Birmingham, still there. Get off and head into Forest Park, where there's lots of trees, drops back to 79, 78, maybe 77. Causes more trees, more grass, and fewer big buildings. Okay? So we're just outside the heat dome kind of. Buildings and pavement absorb and emit solar radiation differently from natural vegetation in the landscape. And like I said, the local climate is a microclimate, can be associated with a single tree. Lichens and moss grow on one side, not on the other. That would probably be on the north side, not on the south side. Other places, it might be on the south side, not on the north side. If you're in a very cool climate, they may grow on the south side of the tree and not on the frigid north side. Down here, they're more likely to grow on the north side where they're in the shade and the moisture doesn't get evaporated away. So yeah, it can vary wherever you are. All right, now the climate change. This is 23.4, and I think this author has sort of a bias here, and I probably have a bias too. But he doesn't seem to be particularly impressed with the concept of climate change. And part of the reason is we've had big, major climate cycles that go far longer than our recorded history. So it's hard to say what's happened in the last 100 years, whether that's really a huge impact or not, because most of the patterns are thousands of years in the making. So that's, I think, part of the reason for his skepticism. And the fact that we haven't had recorded history, they show here reasonably good climate data only starting around the 1500s. Okay, that was the time of 1492. Columbus sailed the ocean blue. Well, the actual exploration started a little bit earlier than that. That's when people started paying a lot more attention to it. Sailors had to. They started reporting things and stuff. Our technology got better. So we've got a lot better data here. This probably didn't look like this, okay? It probably had just as much variation as this does. We just didn't have the data to support it. Who was collecting weather information at 1000, at 1200? I mean, these were the dark ages, the middle ages. People just weren't into that. They were just surviving. That's all they were doing. So that's part of the issue. We had just a very small window where we've actually been collecting the data. Otherwise, it's proxy data that was infer past climate conditions. That just gives us a broad, general idea of what was going on. And still, we're not even into the ice ages back then. They started even way before this, okay, and ended way before this. So it's really hard to say. But this is the part that really bothers people. Looky here, I mean, you got variation and stuff like this. If you get here, phew, that is a long, sustained, and then a little blip here, but still a long, sustained, really rapid change of climate information. That's what people are worried about. Where are we talking here? 1900s. What happened in the 1900s? Shortly before, shortly after. Industrial Revolution. That's when, before this, agriculture. Most everything was dependent on agriculture. They had some industry, but not much. Most people were farmers. Most people were living on the land. Not that many in the cities. Industrial Revolution, big factories, big mass movement away from the farms to the cities to get those good, supposedly good paying jobs. And industry picked up. You had, before this, basically you burned wood. That was your heat source. After this, you're burning coal, you're burning gasoline, fuel oil. It's just everything changed about that. Yes.
What about jet air travel?
Oh yeah, I didn't. Nothing back then. No, watch it.
Be it by itself, because you're up in the atmosphere.
Yeah, but I mean that's really pretty minuscule compared to automobile travel. I mean, it is way more than it used to be, but nothing. I mean, some people say, "Well, we're firing rockets into space. That has to be messing up our atmosphere." Well, maybe a little bit, but we just really don't fire them that frequently, you know.
If you think about automobiles, we're on the ground, but planes are in there.
Yeah, they are. Yeah, I know what you're saying, and that it definitely could be a deal there. But if you
and
just
then the models that they do,
oh yeah,
the ocean level will rise an inch over 100 years. Man.
okay, and sure we've had ice ages before, and things got quite warm after ice ages, but that takes thousands of years. You know, it did. This is happening in half a century or 1 century. No, you don't see that big a change in that short a time. Of course, we don't have the data to show back then, but that's the thing that bothers people. So the next slide shows a much smaller range from 1900 to 2000. This describes that peak right there that we were talking about, but they changed the scale on us big time, okay? The data about the ice ages and interglacial warming show that periods of warming and cooling occur in large cycles. Nothing like a little 100 years, okay? But during the past 100 years, the Earth has experienced 2 warming cycles. One in the early 1900s, and then another one again in the, say, the 1960s to 2000, and that's continuing. This is that little blurb that we saw there. Now, this change of temperature, this zero here, I think is very different. Oh, maybe not. I don't know. It's hard to say. See, that only goes to 2000. Yeah, I don't know. I have trouble resolving this, but this is changing temperature in degrees Celsius, negative 0.4 to positive 0.4. Let's see what the scale is here. This is 0 to 0.5 is way up there. Okay, so I don't, yeah. See, that line probably starts in late 1800s, so you don't see that here. But, yeah, so this is much more refined data than what the last one was. Temperature changes are not uniform, okay? Temperature changes in the southeastern U.S. have cooled since the early 1970s. I sure don't notice that. I mean, I lived in the southeastern U.S. during the 70s, and I did not notice it was any hotter than it is now. Sea ice in Antarctica, has increased, it says, but I believe that since this was published, not the case anymore. See if he says that here. Yeah, he's not saying that now. In his last sentence in this section here says, sea level has increased 1 to 2 millimeters per year in the past 100 years, and this increase is due to thermal expansion of seawater in addition to melting ice. So both of those factors are there. So he's not saying that it's changed, because I think that turned around. All right. Causes of this global climate change. And sure, I agree with just about everything he writes here. Results of the this is a result of complex interaction of many, many factors. I think Ricky was mentioning sunspots, weren't you? Or was it you, James? Okay. Somebody I thought mentioned sunspots. Maybe it was in one of my physics classes. Someone was mentioning that. Yeah, that can have enormous influence. And the sunspots sometimes are very active, sometimes not. And that can make the Earth's tilt, well, that's always been there. The orbital shape, that hasn't changed much. The wobble is a very slow change. So, yeah, these are complex interaction of all these things. The greenhouse gases, that's the thing people are worried about now. Now, water vapor's always been there, so I wouldn't make that a big deal. It's the carbon dioxide, methane. Now, there's other trace gases. And sure, carbon dioxide and methane make up a very small percentage of the atmosphere. But, even though they're small percentages, that has greatly increased in that small range. And this is another one I think is really, really important. Tropical deforestation. And I think we talked about this in an earlier class. Brazil has been notorious with this. They were trying to feed themselves, and they took down tropical rainforests like crazy, because the soils there were pretty decent because of all the organic matter. So they took them down. They couldn't use all the wood, so they just pile it up and burn it. Well, that's releasing tons of carbon dioxide into the atmosphere, whereas before the tropical rainforests were trapping carbon dioxide like crazy because they're tropical rainforests and giving off lots and lots of oxygen. In fact, most of the oxygen released for us to breathe probably comes from the tropics, where they have the rainforest. Our trees, we have lots of trees, but you know, we have lots of population too. And we count on them. And then not only that, then they grew soybeans for maybe 5, 10, 15 years. And then those soils, they used up all that good organic matter that was there because of the tropical rainforest. And those soils turned into bricks. Once that organic matter was gone, the usefulness of those soils were almost depleted. And then they had to cut more forests to get more of the crops. Okay? They left behind not a place where forests are going to grow back quickly, because that soil is in miserable shape now. So we have done some pretty dumb things. Our digging up the grasses in the Great Plains and creating the dust bowls we talked about earlier. Not a very smart move, okay? The Great Plains just cannot support intensive agriculture like we thought they could. We just happened to develop, get there at a time that was sort of a rainy season, unusually rainy. We didn't know it was unusually rainy. We thought, oh, this is great farming, until it turned back to its normal dryness, and then we couldn't support it at all. Now, what else we're doing? We're pumping groundwater, and if we had time for the next chapter, we'd talk about this more. We're pumping groundwater out of the ground at unsustainable rates so we can keep doing agriculture. Not a good idea, folks, because once that groundwater is pumped out, what sometimes happens where the groundwater was, the land now caves in. And if it caves in, even if you get more rain, there's no place for it to go. So these aquifers that are underground, if you let them cave in, they'll never replenish. I don't see how they could possibly reshape themselves. Everything goes downhill, right? Soil too. So yeah, there's a lot of factors I think man has done that has changed climate. Whether it's as badly as some people claim, or definitely not the other. Now, global warming, and this is where the guy sort of gets on my nerves a little bit. The Intergovernmental Panel on Climate Change, IPCC, established by the United Nations in 1988. That's pretty recent, okay? Admittedly, that's a very short time compared to the eons of time that the Earth has been here. Now, here's his statement. Despite research, data, and models, the predictions of the experts vary. And this probably was more true when this slide was produced than it is today. However, the people who argue against it are still referring to a handful of experts back then that were saying something different from what the vast majority are saying. So it actually has gotten, the variation is much less than it used to be. Now, this is a statement that sort of bugs me. Critical analysis of the climate change should be completed before future policies about human-made carbon dioxide are implemented. How critical do you need to be? Okay? How thorough does that analysis need to be? By the time we nailed it down that yes, we have created this, we may be too late to make any change. Okay? So I do not agree you can't start some policies until you get all the data in hand, because by the time you get all the data in hand, it may be too late to make a change. Here is, this is not talking about climate change, but I think it could be. We are using fossil fuels at an exponential rate. Okay? Not a linear, not a polynomial rate, not a power. We're using exponential. I mean, every so many years, we're doubling our use of those fossil fuels. Guess what? There's a limited amount of fossil fuels, okay? Those fossil fuels took tens of thousands of years to form, okay? Now, maybe there's a lot of it still down there, but we're using it faster than it's being formed, for certain, okay? Now, an exponential growth means things can get out of hand really quickly. Did I tell you this illustration of the Indian mathematician who made a chessboard? Have we talked about that before? Supposedly this Indian mathematician was the one who developed the game of chess. Okay? You're familiar with the chessboard. There's 8 columns and 8 rows. 64 squares on the chessboard. Okay? Well, he developed this, and the knights and the kings and the bishops and the rooks and the pawns and all this stuff. And this big, powerful Maharaji in India fell in love with this game. He said, find me the man who invented this. I want to reward him. I've never had anything I enjoy doing as much as playing this chess. So they searched around and found this little mousy little mathematician and said, Maharaji wants to see you. No, not lowly meet. No, he wants to meet you. So he went to the court and said, oh, Saeed, you honor me so much. No, you honor me. This game is tremendous. I want to reward you. Name your price. I will give you anything within reason of my kingdom. Name it. You have done a tremendous job of this game. So, oh no, just the fact that you love it, that's more than enough reward for me. Nonsense. Name your price. He said, okay, here's the chessboard. If you'll put a single grain of wheat in this first square and double it every square. So second square has 2 grains, next square has 4 grains, next square has 8 grains, next square has 16, and on like this. The first row you had maybe 100 and some grains. He said, no, I really want to reward you. He said, no, that'll be enough, just that. So he said, okay, finally, okay. Well, doubling every square before he reached half of the chessboard, he would have emptied every granary in his kingdom. Before he got to the 64th, he would have had more grains of wheat than had ever been grown on the planet since the beginning of time. Okay. Exponential growth takes off and goes, even if it starts really slowly, because we're in the middle of it. Now, admittedly, we've slowed the exponential growth. Used to be we were probably doubling the amount of fossil fuels we had used probably every 5 to 7 or 15 years. We may be up in the 20s or 30s now. So that we have slowed that rate of increase, but we're still in exponential growth. And at some point, it's going to be, we can't sustain this. We can't find it fast enough and process it fast enough to do it. If we haven't got alternative plans in place, then we're going to be, as they used to say, sucking wind. Okay? It's not going to be anything else. Now, another illustration of that same type of concept is, what if I had a pickle jar? You know what I mean by a pickle jar? My mom used to put up, we raised cucumbers in the garden, and she'd make pickles every year. And the first step was to put them in brine and let them soak there for a long period of the cucumbers. And she had, I think it was a 3-gallon jar. So let's imagine we had that 3-gallon jar, pickle jar, filled with the perfect medium for raising bacteria. Okay? And I'm going to put a single bacterium into that at the day one, okay? Now you tell me, just make up a time it takes that bacteria to double. And that's how bacteria increase. They double. They feed, they eat, and then they split. They feed, they eat, they split. Just like doubling the grains on the okay? So you give me a time. How long do you think it takes for that bacteria to eat that perfect medium and then split and become two? Thank you. 2 days. 2 days. 2 days. All right. Now, let's also say that you know when that jar is going to be completely full. From day one till it's completely full, make up a time. Weeks, months, year, whatever, name it. 2 months. So 2 months it'll be completely full. When will that jar be half full of bacteria? Say again?
Is this the same jar?
Same jar, yeah. When it would be half full. It's going to be full, absolutely full, in 2 months. When was it half full? Say again?
In 1 month?
Okay, no. Well, the doubling rate is every 2 days. It would have been 1 month and 28 days. Because it doubled every 2 days. When it was half full, in 2 days it's going to double again. So it happens quickly that you reach that point of no return, you know. And if we wait until all the critical analysis has been done, that we say, yeah, we do have a problem, and wait then to start implementing future policies, the future may be already there, okay? And we won't have time to make adjustments. So I don't know. I do not care for that statement. Sorry, that was way too much, perhaps. That, folks, was the last slide, okay? Let's see if there's anything else here. Oh, the sunspots, they do show that. They show that illustration of the Earth's elliptical orbit. They have exaggerated that really big time. They exaggerate the tilt of the Earth's axis. I don't think it's going to change that much that quickly in the shape of the Earth's orbit, you know, that kind of stuff. Now, there is a great blurb here on El Nino on page 597. I bet you've all heard of El Nino, right? Do you know and understand what El Nino is? I've read this a few times and I still get confused what it's causing it. But this is well worth a read. One of the best blurbs I think I remember seeing. There is a people behind the science, Wilhelm Thurman Gyllenborg, or something like that. I think he was a Norwegian scientist. I believe he came to the U.S. at some point, but maybe not. Maybe I'm thinking of someone else. But anyway, pretty interesting to read that. Here is that carbon dioxide concentration in the atmosphere since 1860. That is a pretty dramatic change. This is on page 598. Very dramatic. Okay? Now, this was one of the tougher chapters to get a decent test on. So please, folks, this chapter test is not super easy. So do your real good formula equation sheet for this one. The summary here is pretty good, but it's a fairly short. Key terms are about average, about average, because there's some on the next page. The multiple choice questions applying the concepts, there's 45. That's a few fewer than normal, I think, but pretty close. They have the answers, you know. Question for thought, 14. That's about average, maybe a little short. For further analysis, 4. That's probably pretty close to normal. And then there's the parallel exercises. Don't have to do any of those unless you found some of those concepts pretty interesting. But the Group A answers are in the back if you have the full book. But the Group B are not, so you may not want to do that. And I don't guess we have time to start any on Chapter 24, Earth's Waters. Now, the only thing is, there are, I think, 2 questions on the final from that Earth's Waters question, chapter. But I think they're pretty obvious what those are. And I don't think you'll have any problems with identifying. If, however, you do miss one of those, I won't let it count against you. But the rest of the question, because I've already made out the final, I was hoping we would have a little bit of time to do 24, but like you said, this is a long chapter, 23. So that's going to be it. Any questions? So the first, okay, so let's go over Tuesday. We'll meet here at noon, and I will probably, if I don't have the pizza here at noon, I'll have it shortly thereafter. I usually call about a half hour ahead, tell them I'll be there in 15 minutes, and think that's going to be enough time. They say, oh, that'll be no problem. I get there and it's not ready. So if they are having a busy lunch hour, I may not be able to be back right at noon. Don't go anywhere. I'll be here with pizza, 1 pepperoni and 1 meat lover or something like that. And so we'll do that for as long as it takes you to eat your pizza. Now, you're responsible for your drinks, okay? Just know that there's no alcohol, okay? So, Amber, none of alcohol, okay? School policy. But bring whatever you want to drink. I'll have the pizza. I'll try to get enough napkins. If not, we'll get paper towels. Then we'll have the test of chapter 23, and then we'll have the comprehensive final, which will be pretty easy, okay? And that'll be all, folks. Please do your student course evaluations. If you haven't already, please do that. Appreciate it.
I want to wait to see how easy that test is.
Okay, that's perfectly fine. I'm afraid the chapter 23 is a little bit one of the harder ones, but the final is pretty nice, pretty easy. Most people do pretty well. Good deal. We will have a good weekend. We'll see you on Tuesday.